Welcome. All right, so now we're going to be looking at horizontal asymptotes and vertical asymptotes and how those apply to limits. So guidelines for finding limits at positive and negative infinity of rational functions. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. We saw this. Come on back. I thought I'd be quick and put in a link. There we go. We saw this on this page here. Right? On the first example, notice the numerator has a degree of 1, denominator has a degree of 2. So denominator has the higher degree. And notice that the limit as x approaches infinity is 0. That's also our horizontal asymptote. There we go. If the degree of the, so now let's look at the second guideline. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And we saw that in the second example. So notice that both the numerator and denominator are degree 2. The coefficient of the leading term in the numerator is 2. Coefficient of the leading term in the denominator is 3. Notice that our limit is 2/3, and that's also our horizontal asymptote. And then our third thing that can happen my link seems to work better going the other direction. There we go. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. And we saw that in the third example over here. Let's see if it moves over, where our numerator had a degree of 3, and our denominator had a degree of 2. And the limit as x approaches infinity does not exist, and there was no horizontal asymptote. Right? So we can use the degree of the numerator and denominator to help us find limits. And in a later lesson, we'll actually be looking at some of those shortcuts. This lesson is going to focus on horizontal and vertical asymptotes. And in a day now. There we go. All right, so we've looked a little at horizontal asymptotes. We're going to come back to them. Let's look a little bit at a problem like this. All right, so here, what's happening as x approaches 2? All right, so what's the limit of 2x plus 3 divided by x minus 2 squared as x approaches 2? What do we see from our table? Now, if you just took the average of the limit as x approaches 1.9 and the limit as x approaches 2.1 and thought it was the average of those two, you would be very, very wrong. Because there's a lot of space between 1.9 and 2 and 2.1 and 2. And a lot can happen in 1/10, right, as x gets closer and closer to that value of 2. Right? What do you think might happen here? So I'm not gonna tell you, but I want you to think about what might the limit be as x approaches 2 for this particular function based solely on the table. What's going to happen as x gets even closer and closer to 2? Are the values still going to stay between 680 and 720, or are they going to do something else? And this is very similar to a problem we looked at the very beginning of the year when we were doing numerical limits and being able to figure out based on our function what was really going to happen as x got closer and closer. All right, so let's take a look at a graph. Maybe the graph will help us. Right? So here we're looking at the limit as x approaches 2 from the right-hand side and the left-hand side. Notice that, well, this graph only goes to 10 because it's kind of hard to make a graph that goes all the way up to 700. But notice that from either side here, now they are not going to be meeting together. Right? There's not going to be a turnover point where somehow we reach some kind of finite value. Right? Instead, it appears from our graph that we're getting closer and closer to as x gets closer and closer to 2, our function keeps getting larger and larger. And so does the limit from the graph appear to support what we can see numerically there? Right? I didn't actually give you the results because I want you to think about it. I'm going to give you the final results when we solve it out analytically. But now, what does this appear? What appears to be happening here? It appears right, that our function is going to infinity. Now, that doesn't mean that we have a limit here. Now, limit exists. Right? So we're not saying when we have a limit of infinity, we're not saying the limit exists. It's describing the behavior of the function. So notice from the left and from the right, our function appears to be growing without bounds. Let's try analytically. Right? So the numbers kept getting larger. And notice they got quite a bit larger. So to go from 0 to 1.9, it increased almost 680. And to go from 4 to 2.1, it increased almost about 718 there, 717. Right? So there's a lot of growth that is occurring between 1.9 and 2, and 2.1 and 2, that we don't see in the rest of the graph. Our graph, or I mean in the rest of the table, our graph is seeming to support that. And then when we look here and solve it out analytically using direct substitution, right, and we plug in 2, we see we have a problem here. We have 0 in a denominator, and that is a limit that does not exist. That limit does not exist because there's a vertical asymptote there at 2. Right? And so as x approaches 2, our function is going to keep increasing without bounds. Let's look at this one. Right? So the limit as x approaches -4. Right? So here I went up to -4.5 and up to -3.5. Right? Now what's happening? So notice one side's on the one set of values is on the negative side. Right? So it goes from -2.25 to -8 to -4.5. Then we have that error. On the other side, we're also on the negative side. We got -1.125, 6, 26. What do you think might happen if I were to be closer than half away? What if I was only 1/100th away? What do you think the numbers are going to look like? Let's see if the graph helps us analyze the information from our table. Okay, now we have this particular one, and so notice as we go from the left and the right hand side, our function just keeps growing and growing, and it doesn't look like the two sides are going to reach. It looks like they will be approaching negative infinity. And we'll solve this one analytically now as well and see, is this something that a function that's going to decrease without bounds? By the way, I don't think a lot of these are in your notes. I gave my copies away because these are just some examples. I had the beginning part, but not this part in your notes. So here we're looking at the limit as x approaches negative infinity. And now what we're going to do is solve it analytically. We can plug a value in. Notice we have 0 in the denominator again, which does not exist. And that supports what we have here with the vertical asymptote. And here with our table, our values don't seem to be approaching anything. They just seem to be getting smaller and smaller. And actually, so here it's kind of, I'm trying to look at my values here, and so I did just plug them in. They're a little more difficult to look at them. I go from -2.5, -8 to -4.5. I'm kind of wondering if I don't have two of my values reversed. Let's see. So I have a feeling, oops, this kind of stuck in there. I have a feeling these two values are reversed because it should be getting smaller and smaller as we get closer to -4. So as I'm looking at this, I have a feeling that, you see how it's stuck in there? It got stuck in the wrong place, and I got a feeling that those are reversed. I'll calculate it out later. Right now, it's a little more important that we just kind of compare our table, what we see in our graph, and what we get when we solve it analytically. So vertical asymptotes. So we're going to find the vertical asymptote of the graph of f of x and describe the behavior of f of x to the right and left of each of our asymptotes. All right, so we can look at the graph to see what the vertical asymptotes are, or we could just factor, right, our denominator there. If we factor, that is a difference of squares. I could write it as 2 minus x and 2 plus x. Usually we have the x first, right? But I'm not going to factor out that negative. I'll just factor it just the way it is. Right? And so if we set those equal to 0, 2 minus x, used to writing x minus 2. Erase, erase. So if we set 2 minus x equal to 0, then negative x would be negative 2, which would make x 2. And if we set 2 plus x equal to 0, then, and subtraction 2 from both sides, x is going to be negative 2. Yep. Started to write my x and it came out funny. Oops, now we lost part of it 2. X is equal to negative 2. All right, so those are our vertical asymptotes. X equals negative 2 and x equals 2. How does this relate to the limit? So actually, I think this whole graph is in your notes, and we're going to fill this part in and look at how this is going to relate to our limits. If we look at our graph and look at the behavior as we get closer to each of the limits, notice over here that our function is approaching negative infinity, and I'm going to actually write this as a limit. So the limit as x approaches negative 2 from the left-hand side is negative infinity. Over here, our limit as x approaches negative 2 from the right-hand side is positive infinity. Here, our limit as x approaches, so now we're approaching 2. I probably should have done this one first. I'll do this one first. So this one over here is the limit as x approaches 2 from the negative side, and that's infinity. And then the limit as x approaches 2 from the positive side is negative infinity. So here they're going opposite directions from the left-hand side and the right-hand side as we get close to both our asymptotes. They can go opposite directions or they can go the same direction. Right? If a function's always positive or always negative, they're going to go the same direction. So other functions have vertical asymptotes, trigonometric functions, such as tangent. And actually all of them, other than sine and cosine, are going to have vertical asymptotes to think about. And last one is cosecant x there. So those all have vertical asymptotes. Logarithmic functions all have vertical asymptotes. So let's think about how this is going to relate in terms of the limits. All right, so, and you can put this part in your notes. No, actually, you can put the other parts in there too. The vertical asymptote, we know we're going to have a vertical asymptote when the limit as x approaches a constant from the left-hand side is approaching infinity or negative infinity. You put a place for my plus minus. And, oops, the limit as x approaches some constant from the right-hand side is equal to positive or negative infinity. All right, so notice I have this two one-sided limits. And notice when I was describing the behavior of my function here, my rational function, I had all one-sided limits. Well, there are lots of functions whose limit as, actually that would be as limit as x approaches infinity, excuse me. So when we're talking about vertical asymptotes, we're looking at our one-sided limits as x approaches from the left-hand side and the right-hand side. Now those don't have to go to different ones. One could go to positive infinity, one could go to negative infinity, or they could both go to positive infinity, both could go to negative infinity. Right? But we're looking from either side what's happening. Right? So sometimes we have vertical asymptotes from the left-hand, we'll have vertical asymptotes from the left-hand side and the right-hand side. What are they approaching? That also applies to our logarithmic functions, right? So when we think about a logarithmic function, we're only going to approach from one side. So when we're talking about vertical asymptotes, we're going to be looking at limits as x approaches some constant value, so some finite value, right, from the left-hand side and the right-hand side, or the left-hand side or the right-hand side. It could be one-sided, but we're looking for a limit. We're looking for our function to be approaching positive or negative infinity. Okay. So let's take a look a little bit more at vertical asymptotes. Right, so that part you can put in your notes, and I think I have almost the same thing on the next page. I think. I believe I wrote it one more time again. Yes, I did. All right, so here where you have a little space there, whoops, come back to the other side, about where we're talking about how this relates to the limits. And then I'm going to define it more formally, which is right over here. Right, so a vertical line x equals a is called a vertical asymptote if the limit as x approaches, I used a on this one, a, c, constant. From the negative hand side is infinity. The limit as f of x, the limit of f of x as x approaches a from the negative side is negative infinity, and the last one I put positive and negative just to make it a little simpler. The limit as limit of f of x as x approaches a from the positive side is infinity, or the limit of f of x as x approaches a from the positive side is negative infinity. Right? So these are all one-sided limits as x approaches a. And if that limit is positive or negative infinity, that's going to show that we have a vertical asymptote. Right? So note a graph can have an infinite number of vertical asymptotes. It can have at most only two horizontal asymptotes. You can go to positive infinity, you can go to negative infinity. Horizontal asymptotes describe the left and right hand behavior of the graph. A graph will almost never touch a vertical asymptote. However, a graph may cross a horizontal asymptote. And I really, off the top of my head, can't even tell you one where we're going to touch a vertical asymptote. You just don't encounter them very often, or at all. So the horizontal line y equals a is a horizontal asymptote if the limit of f of x as x approaches negative infinity is a, or the limit of f of x as x approaches positive infinity is a. And so in all of these, a or c is some constant value. I'll put that in there. So here a, c, etc. is a finite constant. Some finite constant. So notice in the vertical asymptote, it's the limit that's positive or negative infinity. For the horizontal asymptote, it's what's x approaching that's negative or positive infinity. Right? So they're kind of flipped of one another, where the finite number is and where positive and negative infinity are. Right? So we're going to look just a little bit more at vertical and horizontal asymptotes. And actually, that's what the whiteboard practice will be, all about vertical and horizontal asymptotes and how those relate to limits. This is in your notes, right? So we have a vertical asymptote here at C, which is really, really faintly drawn. I don't know if it's better on your notes than what I can see up here. I will draw it in a little bit darker. You might want to draw it in darker. Right, so, but everything else is in your notes. There are 12 situations involving limits and infinity, as we have illustrated below. So these are the different ways that we can have either a limit that's equal to, all the different ways we can have a limit that's equal to infinity or negative infinity. Right? We could have a one-sided limit as x approaches some constant, right? Where our function grows without bounds. So here our limit as x approaches, a left-handed limit. Here we have the limit as x approaches c from the left-hand side of f of x is infinity. Right? So we're growing without bounds on one side. And an example of a function like number 1 would be a logarithmic function. But in this case, it would be a logarithmic function that's been reflected. Right? So usually they look like this. Here we have one that's been reflected. That would give you that shape. Here we have the same kind of idea, but our function as x approaches c from the left-hand side is approaching negative infinity. Right? So here are two examples from the left-hand side. Now let's look at the right-hand side. Here we have our function is approaching, as x approaches c, our function is approaching infinity. from the, as x approaches c from the right-hand side, our function is approaching infinity. Right, here is our vertical asymptote again. Oops, I just crossed my own function. So if you can't see these very well in your notes, then just feel free to darken those up. There's our vertical asymptote, right? So here we have an example of a limit as x approaches c from the right-hand side of f of x, where our limit is negative infinity. And any one of these, 1, 2, 3, and 4, could be represented by a logarithmic function. This would be, number 4 here would be your typical logarithmic function, like, for instance, y equals natural log of x, something simple as that. All right, that would have that shape. Right? If I make it negative, so if I have y equals negative natural log of x, it would look like that one. Right? And for this one over here, the number 2, if I had y equals natural log of negative x, it would look like that. So these are all just examples. They are not that particular graph, but these are examples of graphs that would have this shape. And this one here would be y equals negative natural log of negative x. It's been reflected twice. Negative natural log of negative x. Right? And that would have that particular shape. So here's one. Here are 4 examples, just with the natural log of x and how one little negative will change that shape. All right, so now we're approaching infinity or negative infinity from both sides of the two-sided limit. So we have the limit of f of x as x approaches c from the right-hand side and the left-hand side is equal to infinity. We saw that with some of the functions that we were just looking at a couple pages ago, literally. So for instance, this one, if I go back like 3 pages, right here. I'll go back to the picture. All right, so here with that, here with the negative in front, right, that one approached negative infinity from both sides. Without the negative, our function approached positive infinity from both sides. And that's because that denominator was always going to be, that stuff in parentheses there, the squared part, was always going to be positive. And so now that negative is going to change whether it's heading positive, whether it's approaching positive or negative infinity. All right, so here again is our vertical asymptote, and there are 2 different shapes. Both of these are going to be rational functions. And either the numerator or the denominator has to be, we have to have something to an even power. Right? So to get them both to go the same direction, there must be an x squared or x to the 4th as the leading term. In the numerator or denominator. Right, so there would have to be. Right, that's what would make it go the same direction. Right, so here are just some things to help you understand and kind of recognize these shapes and other functions that would have vertical asymptotes. Right, so here we have some more one-sided limits. Now we have noticed that our limit are all constant, or at least constant in the first 2 examples, but it's x that's approaching positive and negative infinity. Right, so here we have a horizontal asymptote as x approaches infinity, right? And we have our function's approaching a constant value, so that constant value becomes our horizontal asymptote. So here, I don't have it written down, but L equals horizontal asymptote. Only 2 of them have that. Right, so but that would be, our L here would be a horizontal asymptote. Right, and so an example of a function that would look just like that would be, for instance, y equals, oops, that was supposed to be equals. However, what I'm thinking of involves an e. So y equals, this is an example, y equals negative e to the x. Right? So we're reflected, and actually this one would be plus something, plus L in this case. That would give that horizontal asymptote of L there. Without L, but plus L, its horizontal asymptote would be 0. Right? And so these horizontal asymptotes are a little easier to see, at least. Right there's our horizontal asymptote. It's not very straight. There's our horizontal asymptote. And so here, though, we're approaching negative infinity. Right? So if I have, for this particular function, an example that would kind of match this graph would be y equals, so in this case, I'm going to approach negative infinity. Decay. This would be a decay graph, would look like this. So if I had, and it's reflected, so if I had y equals negative e to the negative x plus L, that would be an example of a graph that would have that shape. Right? So it's decay, so it's going in the negative, it's going in the negative direction to the right-hand side and towards the asymptote in the left-hand side. Right? And it's been reflected. However, here we have, we're looking as x approaches infinity, and our function grows without bounds. Right? So an example of a function that would grow with, would keep on growing as x approaches infinity. Well, actually, if I have y equals e to the x, right? On the left-hand side, it's going to have a horizontal asymptote. On the right-hand side, at least, it will grow. It will keep on growing, right? Or it could be, assuming that this is going to be going somewhere, right? Maybe it goes like this, right? Y equals x to the third. Kind of have that same idea. It's going to grow without bounds as we go to the right-hand side. Right, so here we have a limit of f of x as x approaches negative infinity. Right, and now from the left-hand side, it's growing without bounds. So for instance, if I had, so now this one, right, we're looking now towards the left-hand side, right, and then it's decreasing. So if I have y equals e to the negative x, right, as x decreases, the function would keep growing. Right, because that would be a decay function. Right, here we had, we have no asymptote there, of course, in either of these three examples, actually the 4 examples. Here we have the limit of f of x as x approaches as x approaches infinity. Our function, our limit, is approaching negative infinity. Right, so here, as it keeps increasing, our function is going to keep decreasing without bounds. Right. And this one, this would be actually an example of exponential growth. Y equals negative e to the x. Right? So it's exponential growth because it's growing, but it's going to be growing in a negative direction. And then the last one I have on this page, limit of f of x as x approaches negative infinity, our graph approaches negative infinity. So an example of a graph that would model this would be our above example. I could just move that down. Y equals x to the third, right? As x approaches negative infinity, so does y. It's going to keep getting smaller. Right? So that would be an example of a function that has that kind of shape. So these are just examples. They're not the graph, not the specific graph, but they do these shapes of each of these graphs are the functions represent those particular shapes. Right? I thought this would be a quick podcast. Actually, but it is almost over. All right, so limit as x approaches 5 here. We see that now I've got much, much closer. All right, so now I've left nothing to the imagination on my table here. As x approaches 5, our numbers are getting extremely large at 4.999999, negative 200,000, 5.001, 200,000. All right, so notice they're going in opposite directions. Right? When it's growing that fast, as we get closer and closer, you're going to have a vertical asymptote from the left-hand side and the right-hand side. In this case, it's approaching different directions. So our limit as x approaches 5 from the left is negative infinity. Our limit as x approaches 5 from the right is positive infinity. And of course, the two-sided limit does not exist. Infinity and negative infinity are also a does not exist, right? But we can describe what kind of does not exist. In this case, it really doesn't exist. It's not approaching either positive infinity or negative infinity. It's a one-sided limit. All right, and here we can see if we from the graph and analytically, if we plug in 5, we see we get 0 in the denominator. That limit does not exist. Right? So you have a constant over 0. That is a does not exist. You have 0 over 0. You need to do some simplifying. But a constant over 0, that's a does not exist. Right, so infinite limits as x approaches infinity. If the values of a function f of x outgrow all positive bounds as x approaches a finite number a, we say that the limit of f of x as x approaches a is infinity. If the values of f become large and negative, exceeding all negative bounds as x approaches a finite number a, we say that the limit of f of x as x approaches a is negative infinity. Right? So here, when we say we have that x is approaching, or excuse me, f of x is approaching infinity or negative infinity for our limits, right? That means we're not approaching anything, right? We're just getting larger and larger and larger and larger, or smaller and smaller and smaller and smaller. Right, so let's find each limit here. All right, so we're going to take the limit as x approaches infinity of f of x cubed, and the limit of x cubed as x approaches negative infinity. Right, so as x increases without bound, x cubed also increases without bound. So you can write the limit of x cubed as x approaches infinity. That's infinity. These ones I think are in the notes. As x decreases without bounds, x cubed also decreases without bounds. So you could write the limit of x cubed as x approaches negative infinity is negative infinity. This relates, by the way, to end behavior, which we'll talk about in another lesson. Right? But notice as x gets larger, y gets larger. And that's describing our end behavior. As x gets smaller, y gets smaller. So limits involving infinity. Here we have horizontal and vertical asymptotes. Some examples. Terminal velocity as the time is approaching infinity. Right? So as our time increases, right? Our velocity is going to approach some absolute value. Right? Our raindrop is going to just keep going faster and faster and faster and faster and faster. Right? It's going to hit the ground at some point, right? And so there is going to be some type of terminal velocity or a limit to how fast that could go. So that's a horizontal asymptote. Cost of removing pollution. Right? So as you try and remove more and more and more, right? As that percent gets closer to 100%, it does cost more. Right? And sometimes those costs can be just an extreme amount, right? So at some point you have to decide that 1% maybe isn't worth $10 million more, and that would be a vertical asymptote, because we're getting larger and larger as we approach some constant value. Right? In the first example, right, we're approaching a constant value as x is getting larger and larger. A little difference there between horizontal and vertical asymptotes. So definition of infinite limits is a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Okay, and so here we have an example. This one here is y equals x cubed. So from both the right-hand side and the left-hand side, we're going to have an infinite limit. Right, and so here we have an example of a function with two horizontal asymptotes. I think this is my last page. I have 1, 2, that is my last page. All right, so we're going to finish up these last two problems. All right, so we're going to find each of our limits here. All right, so notice it's the same problem, right, but we're finding it from the right-hand side and the left-hand side. How are we going to find our limit? We're going to divide by, and this I know is in your notes, highest power of x. right, so we're going to have the limit as x approaches infinity. What's our highest power? Of course, it's going to be x, right? And that's going to be the square root of x squared for our radical there. All right, so we have 3x divided by x minus 2 divided by x all over the square root of 2x squared divided by, and that's continuing my radical there, x squared plus 1 divided by x squared. So now we'll simplify. So that's the limit as x approaches infinity. All right, so that's going to reduce 3x over x. That's going to become 3. We have minus 2 over x. Can't do anything with that. We can reduce our square root there. Right, so the x squareds will cancel. We've got the square root of 2, and then plus 1 over x squared. All right, so now we can evaluate. Let's put it over here. So we have 3. Right, so the limit of a constant as x approaches anything is just that constant. We know the limit of whenever we have an x in the denominator as x approaches infinity, that's going to be 0. So we have 3 minus 0 divided by the square root of 2 plus 0. So long as there's an x in the denominator, right, and a constant in the numerator, that limit is 0. Right? So now we have 3 square roots of 2, which I'm fine with, or if you want, we can rationalize, and then you have 3 square roots of 2 divided by 2. Either's fine. Right? So from the right-hand side, that's our limit. That's also our horizontal asymptote. Right? So remember the limit as x approaches infinity for our function. If that equals a constant value, then c is the horizontal asymptote. Right? So in this case, our horizontal asymptote, as we come from the right hand, not from the right hand side, as we approach positive infinity, is going to be, I'll squeeze it in right here. Right, it's going to be that 3 over square root of 2, or 3 square roots of 2 over 2. Let's take a look at as we approach negative infinity. Right, so now, really, basically, it's the exact same operation. Right? So again, I'm going to have the limit as x approaches negative infinity of 3x divided by x minus 2 divided by x all over the square root of 2x squared divided by x squared plus 1 divided by x squared. And of course, that's going to be the limit as x approaches infinity of 3 minus 2 divided by x all over 2 plus 1 over x squared. And of course, that's going to give us 3 minus 0 over the square root of 2 plus 0, which equals 3 over the square root of 2, or 3 square roots of 2 over 2. Or does it? Somehow my negative got lost here. Or does it? So you also have to think logically and not just plug and chug like you're a machine. So you have to think about this. All right, so what kind of values can I spit out of my radical function here? All right, so let's think about the numerator. All right, the numerator here could be positive or negative. Right? If I plug in, say, negative, if I plug in 1, or if I plug in 0, right, for x. Right? So 0 minus 2, that's negative. But what about my denominator? Right? Come up with a value that you could plug in there, and it's not even that we have the radical there, the x squared there, making that always positive. It's also the fact that we have a radical. And with the square root, you can only have positive numbers coming out, right? So when you take the square root of something, you get a positive number. When you square something, right, you get a positive number. When you take the square root, you're going to get a positive number as well if you want it to be a real number. Right? So here, this can only be positive. So as we approach infinity, no problem. They're both positive. What happens as we approach negative infinity? And actually, I should move this over here. So as we approach positive infinity is no problem, right? Because Let's move everybody up. You know, I really could have just erased it and started over again with the one little thing. All right, so as we approach positive infinity, this is going to be positive, and this is going to be positive. As we approach negative infinity, that's going to be negative, but this is still only going to be positive. So positive divided by positive, that's positive. But a negative divided by positive is going to be negative 3 over the square root of 2, or negative 3 square roots of 2 over 2. So you also have to think logically about your function. Right? So in this case, our limits were different as we approach positive and negative infinity, and hence the two different horizontal asymptotes. Sorry, this is a little long. However, we got a lot of content in here. And the last thing I'm going to go over is a standard list of indeterminate forms. Right? So far, we have seen this one. We have seen this one. And by the way, there's also negative infinity over negative infinity. Right? So we've seen those two. We haven't seen the other ones. Coming up in a later podcast, we'll be seeing this one, and a little later on we'll be seeing all the other ones. Right? So I'm going to end this podcast for now, and we'll see which other indeterminate forms we see in the other podcasts. Bye for now.